Hello friends, so today in this session we will see the second law of thermodynamics. So this law is also a postulate, and this law is not has been derived from any prior concept. This is generally postulates. So it is stated as in various forms. So many forms are there, we will see every forms, and all the statements have the same meaning. So let us see the statements. So first is the Kelvin. Kelvin says that it is impossible to obtain work by cooling a body below its lowest temperature. So below its lowest temperature, you cannot cool any body. You cannot obtain any work by cooling that body. So that is one of the big restriction. Now second statement given by Clausius. So it is the reverse of Kelvin. He said it is impossible to transfer the heat from a cold body to cold body to hot body without doing some work. Means if you are transferring that a hot body to cold body, you have to do some work. So this work is only possible if you transfer some energy to hot body. Means you have to waste some energy, then you can do some work, or you can convert heat into work. So this is the reverse of this Kelvin, which is saying the reverse of cold body to hot body, because after transferring some heat to the hot body. So this is the statement of the Kelvin. Third is in terms of entropy. So a small change in entropy, the change may be equal or it may be greater than dq by dt for any infinitesimal process. Like if ds is equal to dq by dt for reversal process we are taking, so this will be equal to this one, and for if you are taking irreversible process, then dq by dt will be always greater than ds. So it may be equal to ds or it may be greater than this. It can't be lesser than the ds. In terms of entropy, so it will be always positive. Or you can say due to spontaneous process, entropy of the universe is increasing and is want to be maximum. So you will get the net entropy will be always positive. That is the summation of entropy of system as well as the summation of entropy of the surroundings. This is the one statement. Fourth statement given, all the spontaneous process, means they are naturally occurring process, are thermodynamically irreversible. Means this process can be reversed. This process, we can reverse this process if you apply the external agency. For example, if you want to flow the water to uphill, generally water flow from the uphill to downhill. That is your own process or natural process. But if you want to flow to the uphill, then we require external agency as an electric motor. Then we can do it. Otherwise, this is not possible. It is impossible to construct a heat engine of 100% thermal efficiency that we have seen in the Carnot cycle. If you have not seen, just go through that Carnot cycle. Carnot cycle is the ideal engine. Even that ideal engine is not giving the 100% efficiency. It is always less than 1. That is, heat can be converted to work. Heat can be converted into work. That is not possible, but you can convert work can be converted into heat is 100% possible. So in this case, some amount of heat is always lost, but in this case we can completely get the heat 100% without losing energy. So this is what the third law. So now we will give the statement, the third law of thermodynamics and the absolute entropy. So when the entropy of the pure substances like a solid or liquid increases, temperature increases. Why? Because the molecular motion increases with increasing temperatures. Its vibrations like translational, vibrational, rotational also increases. Similarly, when the entropy of the pure substance decreases, the temperature also decreases. So Nernst, he observed that entropy of perfect crystalline substance at absolute zero and gave the following generalization known as the third law of thermodynamics. So this is a statement, basically entropy of a perfectly crystalline solid, so it can be pure solid or liquid solid, it approaches zero as temperature approaches zero. Means when temperature is going to zero, then entropy of this crystalline solid will also approach to zero. So like this is the limit of the entropy. So when temperature entropy is approaching to 0 Kelvin, then the entropy also going to 0. And if T equals 0, then entropy will be completely 0. Means this is called as the absolute entropy. In this case, what happens? All the molecules or any atoms motions decreased and there is no thermal disorder. So they are the perfect crystals. Actually, what do you mean by perfect crystal? Perfect crystal means crystals in which the element or molecules are perfectly oriented or properly placed. For example, carbon monoxide 0 Kelvin. You can see this is a well defined, they have located, you can see it, but in this way you can see it, the COC, this is OC, this is OC. This is not perfectly oriented or ordered. So in this case, entropy is not equal to 0 at 0 Kelvin, but in this case, entropy of the crystal of Cu is 0 Kelvin. Now we'll see the application of the third law of thermodynamics. So what is this application? It helps us to calculate the absolute entropy of the pure substances, and these calculations based on the heat capacity measurement. Okay, so we can calculate the absolute entropy at room temperature or at any temperature. So we'll see one example also. How we can calculate the absolute entropy. If the entropy change for a difference in temperature from Ti to Tf, so we can write change entropy equal to entropy at final temperature minus entropy at initial temperature, and this is used when there is no phase transition between Ti and Tf. If there is any phase transition, means shape of the one crystal is changing, then entropy of each transition at a transition temperature should be calculated separately, and their sum gives overall entropy change. For example, say rhombic is converted into monoclinic sulfur. So this is a transition temperature 96 degrees centigrade. And in this case, heat of transition, enthalpy transition is this much joule. So we can write delta S is equal to delta H of this reversible divided by T. So you will get 402 divided by this transition temperature. You will get the transition entropy. This is 1.09 joule per Kelvin per mole. Standard entropy of rhombic crystal is 32.6 and standard entropy of monoclinic crystal is 31.8. So these are different. So we can also write this SR, that is delta S is also equal to monoclinic entropy of monoclinic at this temperature minus entropy of rhombus equal to this mass. So it will be equal. So we can also measure the molar entropy of each phase relative to its value at T equal to 0 by determining the heat capacity from T equal to 0 up to transition temperature, that is 316 Kelvin. So hence we can write in this formula, so change in S is equal to C natural log Tf by Ti. When T equal to 0, so we don't know the entropy value also. However, if difference between molar entropy at 369 Kelvin is equal to entropy of phase transition, then we can calculate the molar entropy of two crystalline form must be same at T equal to 0. If you know this thing, then the molar entropy of these two will be always equal to 0. So based on above calculation, we can calculate the entropy of solid, liquid and gases. So let's take the entropy of solid. So entropy of solid at 0 Kelvin is some S and at T Kelvin is something T. So change in entropy will be your St minus S naught. So we can integrate because this is small. So Cp delta T by T. So as according to third law, entropy at 0 Kelvin will be 0 and entropy St will be Cp by T into T, where 0 to T is the temperature. So we can plot this graph Cp by T versus T. So this graph will come like this. So area under the curve is actually the absolute entropy, and we can calculate entropy, that is from 0 to T Kelvin. So this is the curve under 0 to T Kelvin. So hence we can write this whole expression into the simplified form for the solid. So S is equal to Cp dt by dt or Cp dt by dt, or this can be written as the S is equal to 2.03 Cp log of T. What is Cp? Cp is the heat capacity of the substance at constant pressure, and it's supposed to be remain constant in temperature 0 to T Kelvin. Now let us calculate for the liquid and gaseous substance. So in this case, total entropy of a substance at given temperature is nothing but the sum of all entropy changes which substance has to be undergo in order to reach that particular state starting from crystalline solid at absolute 0. So mathematically we can write, so this is the 0 temperature. So it will be entropy will be S naught, then after T, so it will be C dt by T. Then it will come to as fusion temperature. So fusion temperature will be entropy, this will be your delta H fusion by Tf. Then fusion to liquid entropy, so this will be Cp delta T to T. And for vaporization, delta H of vaporization by Tv. And again for ST temperature, Cp by T. So we have this much from 0 to T temperature, covering the fusion also, less than fusion, liquid, melting point, boiling point, and again after boiling point. So we have this much temperature. So we can plot graph like this also. So this is the graph is Taffy graph. So this is absolute entropy versus temperature. So this is 0. So 0 to this some temperature. Again you can see entropy of transition in within the solid. Then again it is increasing, again diffusion. At diffusion it is again increasing, sharply increasing. So this is your solid state. This whole area is covering solid state. Again liquid, again it is increasing. Then it is into vaporization, entropy vaporization, again gas it is increasing. So for this entropy this one, for this entropy this one, for this entropy is this one, for this entropy this one, for this entropy is for this entropy this one, and no entropy transition will be this one, this is the fusion, and for this much entropy will be your for this one entropy will be your S naught. So all entropy has given. So entropy also varies with temperature. So this entropy with rising temperature starting from absolute 0. Now let us take some important points regarding the entropy. Absolute entropy of internal energy and enthalpy cannot be determined, but absolute entropy can be determined. We cannot determine enthalpy and internal energy, but we can determine the entropy that we have seen mathematically. Third law entropy, it is said that the entropy of the universe depends upon the pressure. So the standard value is 1 bar pressure. Means all standard molar value, that is the standard state we are taking 25 degrees centigrade or 1 atmospheric pressure, are positive. Why? Because it is the rise of temperature of a sample above T equal to 0 will be always increase its entropy about 0 Kelvin. Entropy of the diamond is less than that of graphite. So for graphite is how much? 5.7 joule per Kelvin per mole. For diamond is 2.4 joule. So this is your greater energy, is your less energy, this is your greater energy. Entropy of energy, this is greater, this is less. Why it is greater? Because atoms in the graphite is less rigid. Atoms in graphite is less rigid than that of diamond. So this is more efficiently packed. Diamond more efficient packed, and graphite is not efficiently packed. That's why entropy of the graphite is more than that of diamond. And again, entropy is an additive property. We have to add the properties. Already we have seen the numericals in the Teffy graph. We have added all the impurities, all the entropies. So it is an additive properties. Calculation of entropy changes, that is delta S naught using the standard molar entropy. So for a reaction, this is a reaction A, B, and it's giving C and C, C and D. So change in entropy, standard change in entropy will be entropy of the product, molar standard entropy of the product, and molar standard entropy of the reactant. So this is C into whole, and this is C into this, D into this, A into standard molar entropy of A, and B into standard molar entropy of the B. If you just subtract it, you will get the change in standard entropy. So standard entropy of formation of a compound is defined as the entropy change that takes place when 1 mole of a compound in the standard state is formed from its element also taken in its standard state. In this case, if you take the delta H standard or delta G standard, that is free energy, we will see after this lecture, is taken as 0. But delta S standard, if you take the elementary substance, is not equal to 0. So this both can be equal to 0 in a standard state. But delta S standard state in its elementary substance is also not equal to 0. It is always more than 0. So hence we can say a standard entropy of a formation of compound is not equal to a standard entropy of the compound. So it must have a definite value. Now let us see some exceptions in entropy. So when a rubber band is stressed, entropy decreases. When rubber band is stressed, entropy decreases. What happens? Because the macromolecules get uncoiled and hence arranged in a more ordered manner. In the rubber, macromolecules is arranged in a more ordered manner. That's why randomness is decreasing. Similarly, when an egg is boiled, the entropy increases, means entropy of the raw egg is lesser than the boiled egg. Why? Because denaturation of proteins occurs, resulting into the change in proteins from helical form to random form coil. So in case of egg form, what happens? Random form of protein is coiled from the helical form. So again, entropy increase in boiled egg, because albumin of egg white is your tightly held. It is tightly held due to the helical form. So when it converts to boiled form, it becomes your random. That's why entropy of the boiled egg is increased. So one more exceptions. Contrary to the third law of thermodynamics, there are some solids which do not have zero entropy even at absolute 0. So these are another exceptions. So we'll take only examples like glass solids, carbon monoxide, N2O, NO. These are the neutral oxides. These are the solids which consist of a mixture of others. Other solids are consist of a mixture of isotopes, like example Cl2 at 0 Kelvin. So all these having what? This is your they don't have a zero entropy even at the absolute zero. So these are the examples. Now we'll see some of the numericals. So calculate the entropy change for a rusting of fire according to the reactions. This is a reaction, and external entropy of this all compound has been given below. So use this formula. This is the external entropy of the product minus external entropy of the reactant. So this entropy of the product. This is, so substitute this value over here. This value here. So you on substituting, you just subtract it. So this will come on solving minus 549.4 joule per Kelvin per mole. That is the entropy of the system. What is the entropy of surrounding? So since the reaction is exothermic, so hence surrounding of the entropy, change entropy will increase. So change entropy of surrounding will be delta H of surrounding by T. So delta H of surrounding is how much? So this is given here. This is the energy is given to surrounding. So use this value divided by the temperature. You will get this much value. So total change entropy will be how much? So change entropy of the system, that is this much, and change entropy surrounding is this much. So add it. On adding, you will get the change entropy positive. So since it is positive, the reaction is spontaneous. Next question: the molar heat capacity at constant pressure of oxygen is given by this is average entropy. That is this much is 25.723 plus 12 plus 979 multiplied by 10 power minus 3 temperature minus 38.618 into 10 power minus 7 T square. If the temperature of the system containing 2 moles of oxygen is heated from 27 degrees centigrade to 227 degrees centigrade, and it expands 2 dm cube to 8 dm cube. So calculate the change in entropy. Assume gas is ideal and process is carried out reversibly. So we will for temperature pressure variable we use this formula: NCP natural log T2 by T1 plus NR natural log P1 by P2. So this can be written as the integral form: Cp delta T by T NR natural log V2 by V1. So this is a temperature constant, so we can use the temperature not constant, this is variable. So we'll use the P1 P2 by V2 by V1 by using this one. So again substitute the value of Cp. Cp is given this one. So write the whole value of this one over here. This is the whole value and divided dt by dt. This is the Cp, and V2 is given 8 by 2. So what will happen? So just N is given 2 outside, 2 moles. So take whole value this one, again solve it. This one is this one. Temperature is again 300 to 500. This is the constant will come outside, and this whole value will be written as this one, and this is again this is this one, and this value is given here this one. So 2 is multiplied in every cases. So this 2 is multiplied in, you can see, every case up to this one, and this is separately written this one. Now on solving you will get for this one 2, this is this one, and for this one 2 you can write here plus sign. This will be this one, this will be your this one, this will be your this one. So and this will be your this one. So on solving you will get 53.28 joule per Kelvin. So this is the basically formula. Calculate the entropy change when 1 kilogram of water is heated from 27 degrees centigrade to 200 centigrade, forming superheated steam under constant pressure. Given specific heat of water is this much and specific heat of steam is this much. T is absolute temperature and delta heat of evaporation is this much. So use the formula: delta S is equal to NCP natural log T2 by T1. So N will be your moles, 1000 by 18. This is 1000 gram, 1 kilogram. And Cp is given this much, that is a 4180 18 by 100, and natural log this 373 by 300. So you will get 910.55 joule. Now 1 kilogram of water at liquid is converted to gas at 100 degrees centigrade. So we have to calculate the delta S. So delta S will be your delta H of evaporation by temperature. So this is given, again temperature given 373. So if you solve it, you will get answer. This is given here. Now total change in entropy. So change entropy from T to 100 centigrade, delta S of evaporation, and from this 373 to 473 Kelvin. So for this one again we have calculated, that is NCP natural log T2 by T1, that is this one, and delta H of evaporation of this is over here, and for this one again NCP delta, so dt by dt. So it will again come natural log T2 by T1. So for this again Cp is given, the value of steam you can see here, this one 17670 plus 0.49 T. So we substitute value over here, that is the specific heat of steam. So now on solving you will get this value For this one you will get this value, so you will get answer 7522.50. So this is the change of total change of entropy, which is nothing but the positive. Now a substance A is converted to C, then C to D, then D to B. So we have given entropy of A to C is this much, 50 entropy unit, C to D is 30 entropy unit, and B to D 20 entropy unit. You have to find out A to B is how much. So since this is an additive property, entropy is an additive property, so add it, A to C, C to D, and D to B. So A to C will be this much, C to D will be 30, and B to D will be minus 20. Since B to D is 20, so D to B will be your minus 20. Okay, so this will be on solving 50 plus 30, 80, 80 minus 20 is 60 units. So D to B is 20 and B to D will be minus 20. This question, so this is a graph is given of ideal gas. So X, this gas initial state is X, it's converting to Y, Y to Z. So this is the one path, and second path is it's coming from X to Z. So we have four options. Which option is correct? So when entropy X to Z, so given X to Y, that is this, and Y to Z, Y to Z. Second, work done will be X to Z is equal to X to Y, Y to Z. Third, X to Y, Y to Z is equal to X to Y, and D, X to Y, Y to Z is equal to delta X to Y. So out of this, only X to Z is correct. This one is correct. Why? Because entropy is additive. So we can take X to Y and Y to Z. So this is correct option. If you see this work done X to Y, Y to Z. So work done X to Y is isobaric is there. So isobaric density matter X to Y, but Y to Z is the isochoric. So this will be 0. So total work done will be your X to Y only. So answer C is correct, B is correct, A is correct, but this is wrong and this is wrong. X to Y, Y to Z. So X to Y is there, but Y to Z we cannot write like this one. So X to Z, or we can write X to Y or Y to Z. So this is not a correct option. Only A and C is the correct option. This is incorrect. Here one is missing, Y to Z is also missing. So these are the answers.